So today, this presentation is an introduction to fracture mechanics. My name is Daniel Ayewa. I have been with stress engineering for about 13 years. I got my degrees, both my bachelor's and master's at Texas A&M University in aerospace engineering. In the time that I've been here at Stress, I've worked on a variety of problems from the upstream, midstream, and downstream industries, and so it's been quite an honor. So here's a brief overview of the presentation we're going to do today. So this is the first of a two-part presentation. Today we will talk about general introduction. We will talk about some motivations for studying fracture mechanics and some terminology. Then we'll go over fundamental principles of linear elastic and elastic plastic fracture mechanics. We'll look at the failure assessment diagram methodology and then present a case study. And then part two is going to be about 2 weeks from now. There we will look a little more closely at toughness characteristics of materials, crack growth assessment, and some code methodologies and inspection, and then other related topics. All right, so let's start with an introduction, and we'll gain kind of a general motivation for studying fracture mechanics. So the study of fracture mechanics was fueled by some relatively spectacular failures. Many of you may have heard about the Liberty ships. These are World War II ships that were built by the US to meet a need by the British as cargo ships carrying goods across the Atlantic. So they used a relatively revolutionary construction methodology at that time, whereby the entire hull was built using an all-welded hull. And initially the program was considered a success because they were able to build these ships very quickly, and it met the need. But all of a sudden, on a certain day, while a ship was sailing up in Alaska, the entire hull cracked in two. And so that was a relatively spectacular failure. A closer look at the design, they realized that there were some flawed design elements. So first of all, the welds, instead of being riveted, they were welded together, so you had a continuous plate. And so a crack originating in one plate could run all the way across into multiple places, and in some cases, across the entire hull. There were manholes and portholes that had sharp corners, which represented stress concentration factors. And in general, when they did testing on some of the plates, they found relatively low toughness in those plates. So obviously there was a need and the motivation to deeply look at fracture mechanics and try to understand what was going on. And some of the research that came out of that became the beginnings of fracture mechanics as we know it today. Another failure occurred on an airline that was flying to Honolulu in Aloha. Aloha Airlines flying to Honolulu when there was a structural failure on the fuselage of the aircraft. It resulted in a portion of the fuselage coming off entirely, and one of the air hostesses, one of the crew, was actually lost in that accident. So fortunately, the pilot was able to land the plane safely, but again, it was not a pleasant experience at all. And when they looked closer at the damage, they realized that there were fatigue cracks that had formed in the skin of the aircraft as a result of pressure cycles that the aircraft sees with multiple takeoffs and landings. And basically it highlighted that there was a relatively poor maintenance and inspection quality program. Now, I remember I was actually on a flight last year at one point, and we all don't like being delayed on flights, but at one time we were sitting on the tarmac and we were delayed for almost an hour. And when everybody was getting upset and antsy towards the end, they finally announced that we would have to deplane because they had found a crack on the surface of the aircraft. So personally, I was glad that they deplaned us in that case, because I'd rather not fly with a crack in my fuselage. Okay, here's another high energy failure. This is a quartz plant, the NDK quartz plant. So they had a process for growing synthetic crystals. So it's a very thick-walled vessel, and they would put quartz along with sodium hydroxide and various other substances under a very high temperature and hold it for about 150 days to grow quartz crystals. Now, the sodium hydroxide represents a corrosive substance against the carbon steel, but there is a passivation layer that's built from the initial reaction of the hydroxide against the steel. And the owners of this vessel expected that passivation layer would protect them from further corrosion. Unfortunately, they did not have a good inspection program, and it turned out that that was not quite adequate. So as a result, they had a failure, a major failure. You can see that the vessel is relatively thick-walled, and so it was a brittle failure. And chunks of the vessel were flying relatively large distances. One piece flew about 650 feet to a nearby gas station where there was a public fatality, unfortunately. Another piece skipped across a parking lot and hit an auto company where there were about 70 workers present and one person was injured. Okay, so cases like this certainly provide a general motivation for why the industry needs to understand fracture mechanics and so the question of why fractures occur. So in general, fractures occur for a number of reasons. You may have a static load event. This is a single load event, maybe a hydro test or an overload. Usually it can be influenced by the presence of a stress concentration factor, which leads then to a failure. Another reason is fatigue crack growth. So this is for a component in cyclic service where a crack grows over time and eventually becomes critical. And the third reason is a series of environmental mechanisms such as stress, corrosion cracking, like we saw in that last example. And high temperature hydrogen attack is another one where you have the influence of a hydrogen environment as well as high temperatures leading to the fracture. Okay, so I want to take a look at a few specific examples of these types of fractures. Each of these examples represent projects that stress engineering has been involved in. Some of them are failure analyses performed by our metallurgical department, and some of them are fitness for service assessments. Okay, so this first one is a frac stack. So this is a stack that was being prepared for a fracking operation, and they had everything hooked up, and they did a hydro test. Well, after performing the hydro test, the stack cracked, and it was a brittle fracture as a result of the overload from the hydro test. And it turned out that the nozzle intersected the shell wall and created a stress concentration at that corner, which was a major factor in the fracture. And when we take a look at the fracture surface, we see that there's a crack origin and chevron patterns which point in the direction of the crack propagation. Okay. This next one occurred on a steam turbine. So this is a steam turbine rotor which had a failure while in service. And so when we look a little closer at the fracture surface, we notice that there's a crack, a relatively distinct crack. It's a fatigue crack on the surface that had grown and eventually become critical and led to the failure. An even closer look at the fracture surface shows that there's a tiny pore right on the edge of the surface, which represents the fracture initiation point. And so really this you know, the pore was as a result of a weld repair, and further inspection showed additional such features on the surface. And so this was basically a miss as far as the inspection of these components in detecting these features before the component went into service. So let's look at one environmental mechanism. So this one is not a failure. It's more of a fitness for service. A series of vessels were exposed to sodium hydroxide, and there was evidence of caustic cracking in the vessels. So they came to us to do fitness for service on the components. And at various points in the component, you can see signs of cracking as a result of the exposure to caustic. So we did a series of assessments to evaluate these cracks. The micrograph shows a branched cracking pattern that's characteristic of some of these environmental mechanisms. Okay, so as engineers, in trying to think about preventing fractures, there are two tools that we have that we can use to try to prevent them. One of them is good design methodology, reflecting a good understanding of the problem. And then secondly, rigorous inspection. So some of those previous failures we talked about really showed a lapse in an inspection program. So, but again, a good design methodology will address things like stress concentrations and avoid them, especially in a service that is known to have maybe fatigue and various other things like that. And a good design methodology will also adequately account for all the loading that the component might see in order to ensure that it has adequate fatigue life. A rigorous inspection program will set the right intervals, will inspect at frequent intervals, and the goal of that is really to identify subcritical cracks before they become a problem so that you can prevent fracture. All right, so let's talk about, let's do a quick comparison about design for strength versus fracture. In general, when we think about loading for a design for strength, the loading is in the form of stress. In fracture, it's stress as well as the crack size, and the combination of these two result in a stress intensity at the crack tip of the component. The limit in strength design is yield or tensile strength, and so usually we're designing against that limit. When we do a design, we want the stresses to be below yield. Whereas in fracture mechanics assessment, our limit is the fracture toughness, which is the critical stress intensity factor for the material. We also have cyclic loading and strength design, which is in the form of SN fatigue. And in fracture, we talk about crack growth analysis. And the two are related. We'll talk maybe a little more about that in part 2. And at the end of the day, the goal is to determine the load capacity of a component. Whereas in fracture, the goal is to determine flaw tolerance. Let's talk about the anatomy of a crack and maybe introduce some general terminology about cracks. So when we think about cracks, we think about the location of a crack. And so in this case, we have, for example, this is an internal surface crack over here. This one's an external surface crack. Here we have an embedded crack, which is partway through the wall thickness. And this one is a through wall crack. So that's about the location of the crack. We also think about the orientation of the crack. These two right here are axially oriented cracks. And these cracks are subject to loads occurring normal to the crack plane. So in this case, that would be the hoop stress, whereas the circumferential cracks are subject to loads occurring axially in this component. And finally, we talk about the dimensions of the crack. And in general, the length of the crack is captured with the dimension 2C, and the depth is captured by A. And again, with embedded cracks, you might have a ligament on the surface that helps you determine how far away the crack is from the surface. Now, when we talk about crack tip opening modes, displacement modes, it's really determined by the loading. We have mode 1 on the left here, where the loading is normal to the crack plane, mode 2, where the loading is in an in-plane shear direction, and mode 3 represents kind of a tearing kind of loading. And so typically we're mostly concerned about mode 1 loading because that generally represents most severe kind of loading. All right, so let's look at a few fundamentals of fracture mechanics. So we'll talk about stress concentration first. So let's consider a flat plate. It's made of an elastic material and it has a hole in it. If we apply a remote stress, then basic mechanics tells us that stress on the edge of the hole here there will be a stress concentration with a multiplier of 3 on the stress. As the ratio of A over B increases, that load stress concentration will increase, and the stress will become higher. And eventually, as A becomes very large, that concentration approaches infinity, and it starts to look much more like a crack. So again, if we consider some body with a crack of length A and a remote stress applied to it, we want to determine what the conditions are at the crack tip. And linear elastic fracture mechanics predicts a singularity at the tip of the crack. And the stress distribution at the tip of the crack can be described using a stress intensity factor, K1. So it's possible to fully determine the stress at the crack tip based on the value of K1 when a remote load is applied. And then this remote load can be related to the applied stress by this equation. Here we have A representing the size of the crack. We have sigma, which is the stress. And then we have this factor. This is a shape factor that depends on the geometry of the component. And all those things contribute into determining what the stress intensity is at the crack tip. Okay, you'll notice from this equation that the K1 varies linearly with the stress. So hence linear elastic fracture mechanics. And in general, when we think about the limit of K1, so how high can we allow K1 to get, it really depends on what the critical K1 is that will cause crack propagation, and this is a material property. Another way to look at conditions at the crack tip in linear elastic fracture mechanics uses the energy approach. Okay? And so the term energy release rate is one that we use to indicate the energy at the crack tip. And it describes the energy available for or released with incremental crack growth. Okay, so when the crack grows by an incremental amount, there's an amount of energy that's released. It's in linear elastic fracture mechanics, it's primarily strain energy, and the units are for the energy release rate are in joules per meter squared. And as before, failure is predicted depending on a critical value of G. Now, the energy release rate can be related to the stress intensity factor using this equation. There's a slight modification between plane stress and plane strain, but this really highlights the fact that the two terms really describe a similar effect or similar mechanism in linear elastic fracture mechanics, and they are equivalent. All right, so in order to evaluate the conditions in a crack, we need to determine the K1. And there are a variety of methodologies for determining K1. We have many case solutions which have been solved and placed in public literature. And these stress intensity factors are based on component geometries. So there are solutions for flat plates, for cylinders, for round bars, for elbows. The type of stress distribution, so it might be a membrane plus bending, or it might be a polynomial distribution, or an arbitrary stress distribution. And finally, depends on the crack geometry. So you have solutions for semi-elliptical cracks, for through-wall cracks, edge cracks, and so on. So these solutions are typically derived analytically, or they can be derived by numerical analysis as well. And there's available in mechanical integrity codes such as API 579 or BS 7910. Okay, so here's an example. This is a solution for a surface crack in a flat plate based on fourth order polynomial distribution of stresses and based on an elliptical crack geometry. And if you look really closely at that equation, you see that square root of pi a term that's used to determine K, and then a series of influence coefficients that go into the calculation. Now, some of these calculations can get relatively complex, but the good thing is that there are a lot of commercial software that make these much more accessible. Another source of stress intensity factor solutions are journal articles and handbooks, which can be used in performing analysis. And finally, it's possible to determine solutions directly using finite element modeling of the component. Now, the good thing about finite element analysis is that it's possible to capture more arbitrary geometries and determine the stress intensity using those. And then it's also possible to do linear elastic as well as elastic plastic fracture mechanics. Okay. All right, so many materials, let's talk a little bit about elastic plastic fracture mechanics. Many materials exhibit plasticity at the crack tip with increased loading. Okay, so this plasticity represents additional energy that goes into the crack, which is not accounted for or predicted by linear elastic fracture mechanics. So it really represents some additional deviation from linear elastic fracture mechanics. In practical terms, we can still use linear elastic fracture mechanics as long as the crack tip plasticity zone remains relatively small. And then in addition, there's still a singularity predicted within the plastic zone, although it takes on a slightly different form. And so another thing to mention is that the stresses at the crack tip are actually finite. They're not quite infinite. So due to plasticity and blunting on the surface of right at the crack tip, these stresses are finite. So when extensive plasticity is present, EPFM or elastic plastic fracture mechanics is required because it has the ability to capture both the linear and the nonlinear behavior. And so we introduced two terms, the CTOD and the J integral, for evaluating stress intensities or crack tip conditions in elastic plastic fracture mechanics. And in general, the failure condition is determined by some critical value, although when you have a lot of plasticity, it may not be a sudden fracture. It may be more of the initiation of a stable crack growth. Okay, let's look at the CTOD and the J integral. The CTOD is a measure of the displacement at the crack tip. So early researchers observed that in tougher materials, when they loaded the crack right before it became critical, there was blunting at the crack tip due to deformation. And they found that the displacement at that crack tip due to blunting was proportional to the fracture toughness of the material. Okay. The J integral is similar to the energy release rate that we talked about earlier, except that it is able to capture both linear and nonlinear effects at the crack tip. So in practical terms, it is a line integral around the crack tip. It's a path-independent integral, and it represents all the energy going into that crack tip. And so as you can see, the units for it are similar to the energy release rate that we talked about previously. So it captures, again, the effect of both linear and non-linear conditions at the crack tip. Okay, so all of these are measures, these terms are measures of toughness, and they can be related to each other. So in the elastic plastic regime, we have a relationship between the J and the CTOD. And then we can also relate the J to the G as well as the K in a linear elastic regime. And as well we can relate the CTOD to the K. And so these conversions are useful when maybe a test is performed as a CTOD and you need to determine the K1, to be able to convert between these modes. And it's also useful when doing FEA because you can determine crack tip conditions in terms of energy and then perhaps convert it to stress intensity. Okay, in the nonlinear regime, the equivalent stress intensity, and we refer to this as a KJ because it's an intensity that's determined based on the J energy, the J integral energy. But it can be used to characterize also and switch between the referring to crack tip conditions in energy terms versus stress intensity terms. So when we talk about non-linear effects, these are typically seen with increasing toughness and at increased loads. And we're familiar with this phenomenon in this load displacement diagram, which shows a deviation from a linear portion on the left here to a nonlinear portion as the loads increase. So we see this in stress strain curves, and even in testing for fracture mechanics, there's this load displacement relationship. So in fracture, equivalently, the K1 deviates from linear elastic behavior as more and more stress is applied due to plasticity effects. And so, basically linear elastic fracture mechanics underestimates the conditions or the energy at the crack tip because it cannot and does not account for energy associated with plasticity and some of those other non-linear terms. Okay. As far as determining the J in the nonlinear range, finite element analysis is a good tool for doing that. Okay, so let's talk about the failure assessment diagram methodology. So a good fracture assessment methodology should consider questions such as, at what load will the component break? Because that's what we're trying to design for. It should consider a question of, how long will it before it breaks if it's in cyclic service. And so we often hear of the term engineering criticality assessment, which is a fracture mechanics analysis that evaluates whether or not the component with a crack-like flaw in it is safe from fracture, but also from plastic collapse. So it considers both of those terms. Now, we haven't really talked about plastic collapse so far, but we will as we proceed with discussing the failure assessment diagram. So such a methodology should consider the different regimes of fracture mechanics. So we have linear elastic fracture mechanics, elastic plastic fracture mechanics, and finally collapse. The methodology should consider different sources of loads, primary and secondary, or residual stresses. And it should also be able to handle predictions based on quasi-static loadings or cyclic and fatigue loading. And so that's really what this failure assessment diagram methodology is. Okay, so here we have a failure assessment diagram. Let's look at some of the features of the diagram. On the vertical axis, we have the KR, which represents a ratio of the stress intensity factor, which we've already determined, against the K1C, which is a material property. And so you can see that when the KR value is 1, that means that the stress intensity at the crack tip is equal to the critical value and the material is expected to fail. On the horizontal axis, we have the LR value, which is a ratio of the reference stress against the yield stress. And in this case, we're talking about the reference stress is an indication of the plasticity or the loading in the remaining ligament behind the crack, and whether or not that will collapse, will experience a plastic collapse. Okay, so you'll notice in this case that the ratio at max LR is not 1, it's actually greater than 1. And the reason for that is because the LR is determined based on the average of the yield and the ultimate strength, because we're really looking for a collapse capacity at this moment. So when doing an assessment, we determine K1 and KR, and then we determine the reference stress and the LR, and that gives us an assessment point, which we can then plot against the FAD. And a point that falls within the boundary of the FAD is considered acceptable, whereas one outside that boundary is not acceptable. So there we predict a failure. Now, if we look more broadly at the FAD, we can realize that it's split into 3 general zones. Zone 1 is a fracture controlled zone, where the failure is due primarily to fracture type conditions, stress intensity at the crack tip, and it's also elastic primarily. Zone 3 on the opposite end is a collapse regime, where the loading is primarily controlled by collapse. And the intermediate zone right here is kind of a mixed mode, where with increasing values of LR, we get more and more plasticity effects. Okay. So the boundary of the FAD in this portion really represents an adjustment to the limit on linear elastic fracture mechanics to account for plasticity effects. And so you'll remember how we talked about the deviation from linear elastic fracture mechanics previously, and the shift, the difference, the change from linear to nonlinear fracture mechanics really is captured in the FAD by this adjustment here to account for plasticity effects. Okay, and it's also interesting to note that the boundary of the FAD, so typically when we do an analysis, the boundary of the FAD is based on a standard failure assessment diagram, which we can find in the codes, but it's also possible to determine a FAD boundary based on stress strain information from an actual material. And it's also possible to do finite element analysis and determine a J-based FAD for a specific component. But overall, the advantage of this is that because these nonlinear effects are captured by adjusting the boundary of the FAD, we can continue performing kind of a more linear analysis when we perform, when we determine our assessment points within the FAD. Okay, so another aspect of the FAD assessment is accounting for residual stresses. Now, residual stresses apply a stress locally at the crack tip, but will generally not lead to a plastic collapse. And so they contribute to the KR values, but not necessarily to the LR. And in physical components, there's a realization that as the loading increases and starts to become plastic, there's actually a mechanical stress relief that will occur to residual stresses that are present. And so the effect of KR with increasing LR values actually diminishes. And so in order to account for this, rather than adjusting the boundary of the FAD again, a new factor, this is a phi factor, is introduced to the K1 contribution from secondary stresses. So then the KR solution becomes primary and secondary stresses adjusted by this factor ratioed against the critical value. Okay, so at the end, we could look broadly at all of these inputs and how they come into the FAD. So we have the crack component geometry in terms of flaw dimensions coming in. We have primary and secondary stresses that are considered as well. And both of those go into making the stress intensity factor, which is the numerator of this ratio here. And then we have the fracture toughness, which is a material property that comes in on the denominator and gives us all the information we need to determine the assessment point on this axis. Then on the horizontal axis, we have the reference stresses against the yield strength, with the ultimate strength, the boundary of the FAD set by the yield and the ultimate strengths. And we also have flaw dimensions affecting the reference stress solution as well. So let's look at a quick example. This is a done in MathCAD, so just to show for effect how complex some of these equations can be. This one is the K1 solution. Now this one is the reference stress solution, and then we have the FAD boundary itself. And so we're looking at a flat plate with an elliptical crack in it. And if we look at this geometry here, we see that the angle represented here really represents the position along this crack tip where we're determining K. The 0 being here, 90 degrees here, and 180 degrees here. So if we look at a few problem parameters, we're considering a 1-inch thick plate. It's 150 inches in length or in width, just so that there are minimal edge effects on the crack. We selected an aspect ratio of 6 to 1 between the A2C and the A, and the critical stress intensity is 100 KSI root inch. Okay, so here we see the FAD solution for this geometry. You'll notice that the yield strength is 38 KSI with an ultimate of 70, with the K1C showed here. The crack dimensions and the geometry shown here, and we're applying membrane stress of 25 KSI on this crack. So I'll start the animation here, and we see the progression of the assessment point, which initially moves up and then over to the right, and it crosses the boundary right about 3.5, just over 3.5 inches in crack length. Oh, by the way, on this assessment, we're increasing the crack size only, maintaining the aspect ratio, but increasing the crack size. And the plot on the left shows the K value along the entire surface of the crack, and we can see that at the 90-degree position, which is at the center of the crack, is where the K value is highest. And so when we do a FAD assessment on this type of crack, we're really looking at the maximum K across the entire crack in order to determine what the critical value is. And so when performing ECAs, we often present the results in the form of a critical crack size curve. And so here we have the length shown on the horizontal axis. We have the depth of the crack shown on the vertical axis, A, and then a curve which basically represents a boundary that determines acceptable or unacceptable crack sizes. So basically, sizes that are below the curve are acceptable, and sizes above the curve are unacceptable. So these curves are determined based on a series of failure assessment diagram assessments for different aspect ratios in order to capture the different points along the entire curve. Okay? And the results of these analyses are often useful for setting inspection acceptance criteria. So you can take this curve and go into the field and perform an inspection on a component with a similar geometry and determine whether a crack that's detected from the inspection falls on this side of the curve or on the outside of the curve. Okay. It's also possible, as we look at this curve, we'll see that as the length of the crack decreases, the allowable depth is actually increasing. And eventually we'll get to the point where the crack goes through wall and is still stable. And that's considered a leak before break condition. So typically that's a preferred mode of failure because it's possible to detect the leak before the crack becomes critical, and therefore you can do something about it. Okay, so these critical curves can be determined for any combination of component geometry, loading, toughness values, and at the end of the day, it represents a solution about the condition of cracks in the component. All right, so finally, we will look at a case study. In this case study, we will consider a steam pipe. So a client came to us and called us out one day of the week, and they really wanted us to come out quickly because they took off insulation on this piping and found this. And so obviously the conditions don't look very good, and they wanted to know immediately what is the condition of this crack and how do we address the situation. So if we look closely, we see that we have through-wall cracks in these girth welds that are about just under an inch in length. And this is what the system looks like overall. It's a piping system at a plant. The pipe OD is 24 inches with a 1/2 inch wall. And the pipe is made of A106 material with elbows made of A234. And the design conditions are that the component operates at 250 psi of pressure with an operating temperature at about 410 degrees Celsius. Now, the good thing about that is it's relatively warm, and that's generally good for toughness in carbon steels. We'll talk about that a little more in part 2. So let's look a little bit at the inputs that we considered for the assessment. So the geometry we're looking at here in this case is a cylinder, and we just used membrane plus bending stress distribution through the wall. This is primarily the hoop stress. So because the cracks are axially oriented, they're subject to hoop stresses, basically. And then within that weld, we have residual stresses. as a result of the crack being in the weld, but we also evaluated the base metal where there are no residual stresses. And then the crack geometry is a through wall crack. So we estimated the fracture toughness based on upper shelf behavior, and in general, our overall objective was to evaluate the criticality of these through wall cracks so that the client can determine whether they needed to address it instantly or whether they could apply a clamp and continue operation before making permanent repairs. Okay, so let's look at some of the results that we found from our analysis. So first of all, we generated a critical flaw size curve for this component. We also did a through wall crack geometry assessment right here. That's represented by this red line. And so as you can see, the assessment point, which represents the detected flaw, falls to the left of the through wall crack size limit. And so that explains why this crack, which is in service, is through wall, the system is under pressure, but it hasn't gone critical. There hasn't been a failure. And so, by the way, these results consider the presence of the residual stresses within that weld. Okay, so again, the detected through wall length is less than critical. So when we look at the same solution, this time we're looking in the base metal, we see that the critical crack size curve has shifted up. We no longer have a residual stress, and so the crack has a little bit more of an allowance on the critical crack size curve. And more importantly, the through wall solution has actually expanded quite greatly. And so the margin to the critical flaw size grows significantly when we transition into the base metal. And the crack driving force is diminished. So that really explains to us why, the crack which grew or initiated and spanned that weld did not progress further into the base metal. And that gave kind of a general indication that the component was not under imminent failure concern. And so they were able to put a clamp on the component and plan a repair at a later time. Okay, so that's basically wraps up the core of the presentation. Fracture mechanics, hopefully I've been able to introduce to you some basic terms of fracture mechanics, and as we can see, it's a pretty mature assessment technology, or it has mature techniques which are very useful for solving practical problems in design and fitness of service. We can look at problems in the linear elastic range all the way to elastic plastic range. We can look at fatigue conditions at the crack and even environmental cracking mechanisms. So that wraps up the presentation. This is just a recap about what we're going to cover in part 2, kind of loosely speaking. So we'll talk more about toughness characteristics and perhaps how to estimate toughness. We'll talk about how to do assessments of fracture mechanics when there's crack growth involved. And we might talk a little bit about inspection, codes and methodologies, and then other related topics. Okay, and so that really is the end of my presentation. Thank you for attending.